So quickly, before we move to trigonometry, my friends, let's remember what is that thing called product rule. By definition, the derivative of a product will be written this way. I do hope that you actually will try and understand the geometric approach, because that is just, that's how you know that you are seeing something with your eyes. By definition, we see z and here together and x is together, but we realize that if I have a mixture of x and z, I will be able to separate. I'll be able to factor g of z in this case, and f of x in the second part, right? So that is this. I can factor out into this, and this. I can factor out into this. I went over that during the last lecture. I hope you understand that if you are walking in the forest and you do not have a dead reckoning, if you're just walking aimlessly, you don't arrive anywhere. So what you try to understand, and we practice that afterwards in office hours, you need to recognize what somebody is really doing, right? So limit z going to x, f of z minus f of x over z minus x is the definition of the derivative of f. And then we have a similar definition for g. So within this new formula, where we don't know what to do about the derivative of a product, we are trying to find the definition of derivative for g and for f. And I realized that if I introduce the mixed term, I will be able to factor it out, and I will be able to calculate the derivative limit. Here it is, right? And then we mentioned there is this minor hiccup that most people miss. The derivative of this part is the derivative of g times the derivative of the limit of g times this limit here with f. And as z goes to x, g of z becomes g of x. That's because g is differentiable and therefore continuous. So I can just replace z by x. And here I have this derivative formula, which is very easy to remember. I think of it as a traveling salesman. The prime moves from the first function to the next. So just to be sure that you are able to carry out differentiation, let's quickly do one calculation, okay? We can do many calculations, as many as you like if you stay in office hours. So I want you to take the derivative of root x multiplied by e to the x, using this new shortcut. Go ahead, calculate as fast as you can, please. Thank you, Christian. Okay, that's good. So quickly, guys, quickly, so we can move on to new things. Good, wonderful. So here is how you solve it. It's simply the derivative of x to the power of 1/2 times e x. And we can label, we know that we need to take the derivative of the first function. So this is simply the derivative of x to the 1/2 multiplied by the second function plus x to the 1/2 times the derivative of the second function. Good. And e to the x, actually, its derivative is very simple. So this is very quickly 1/2 x to the minus 1/2 e to the x plus x to the 1/2, and the derivative of e to the x is still e to the x. So that's our answer. Good. I'd like to mention a few things, guys. So here is what we truly verified with the power rule, right? We remember we had x to the power of 5. We know that if we take the derivative of x to the power of 5, it's 5 times x to the 4. You remember that Nightingale in the Rose business, right? So we proved it by factoring a difference of n powers. If you are dealing with any integer in particular, so it's x to the power of n, where n is a positive integer, take the derivative. It happens to be n. It happens to be nx to the n minus 1. Yes? That's for any positive integer. Now, it's a slightly different situation. Oh, Nassim, what do you want to say? I'm sorry. Go ahead.
Sorry, Professor, for interrupting you. So with this one, it will be 20x to the power 3, yeah?
If I take another derivative, yes. So this is a derivative of x to the 5 once. It will be 5x to the 4. And if I take the derivative again, it will be 20 times x 3. Yes?
Okay.
Good. I just wanted to take derivative once. I'm just reminding you of the power rule. It might be something that you don't particularly bother, just learn the power rule. I just want you to be very, very perceptive. Yes, so here, so we have this this derivative, and then look at it, guys. When I have derivative like of 1/2, if I take that derivative, it does not immediately follow, right? You have to kind of, it's not an integer, you agree? So you have to establish this using another proof. But it happens to be the case that it's 1/2 x to the power of 1/2 minus 1. The rule still works. Then if you notice, if you have x to the power of minus 5 and you take the derivative of that, minus 5 is not a positive integer. You have to establish yet again, somehow you have to figure out that this rule still holds. It will happen to be minus 5x to the power of minus 5 minus 1. Yes, it will happen to be this to be true. It's just I have to warn you that we have not established it in this class, right? We only established for integer powers, for positive integer powers. Then we can easily from there establish for fractions like this, and then we can do it for negative numbers. If you can come up with an argument, that's good. In general, it happens to be true, although we haven't established that if I have x to the power of alpha, I take the derivative. Alpha can be any number. It would be alpha x to the power of alpha minus 1. Good. For any number, that's still true. So for example, if I take the derivative of x to the power of pi, that will be, whatever that means, will be pi x to the power of pi minus 1. But we have not established this, right? It's just the power rule has to be generalized. If you're strictly speaking, it has to be generalized for and you have to show that this is still so. Good. All right, so that's why here I use product rule, because look at it. This is x to the 1/3 times x squared. You could have actually said it. You can actually say that the derivative is, well, it's the derivative of x to the 2 plus 1/3, which is then 1/3 plus 2 x to the power of 1/3 plus 1. And I don't need to use product rule. But why do I use product rule in this situation? Because I mean, rigorously speaking, I haven't derived the power rule when the numerator, so when the power is not a positive integer, or maybe in this case I derive it for 1 over a positive integer, but I haven't derived it for other circumstances. 2 plus 1/3 is not a positive integer, so I have to be careful. Maybe my power rule is no longer working. Of course, if you're too worried, I mean, in this class, again, right, it ends up being the same as I mentioned. It ends up, if you just are asked to calculate this derivative, you can do it any way you like. I just hope you notice this, this one point that I made. It always, so again, here is what I'm trying to say, guys. Here is what I'm saying. Okay, are you listening? And don't be confused. So the power rule ends up working for any number. It ends up working for any power. But, you hear me, Alisa? But I have not, you see, you have to be worried. I want you to really approach it always from a critical point of view. Know what you have established and why something works to the best extent possible. We have not proved that the power rule works like it should. Okay, anything that you haven't proved, you should always remember to be worried about. Okay, does it make sense, guys, what I'm saying?
Can you explain it one more time?
Yes. So this was not an explanation, right? I say that the derivative of, I say, you can say it's a rule, right? The derivative of x to any power is you drop the power and subtract 1 from it. Negatives work, everything works, right? It always ends up working. But I'm trying to tell you this, guys, right? It should not be confusing to you. Understand, what you should do is you prove this. You understand? We only use what we prove. If you haven't proved it, that means you don't understand why it works. If you do not understand why it works, you should never be surprised that it fails to work sometimes, okay? That something will fail to work. You see, I say rule. I could have lied to you. You know, how do you believe me at all? Do you know me well enough? If I decide to be malicious, I will teach you the material incorrectly. I want you to be paranoid. I want you to be thoughtful. I want you to understand what is it that you know and what is it that you do not know. Good. And Miss Minkowski, welcome. I'm glad that you made it. So let's go back to, so you see, I'm worried. I mentioned this thing and I think I wonder how many of you are confused by such a simple remark. You know, some people don't even understand what is a proof. In other words, they just they go believe in science. I'm not sure what you do, right? A proof is here is a statement. Here is why something is true. If the reason something is true is because your teacher said it, well, okay. Some teachers are not very, you know, smart. They can tell you incorrect information. So there are no rules. It's like the Wild West. And then again, I mentioned F, G, and K. If I take, remember, if I take the derivative of F times G times K, if I want to take F times G times K and I want to take the derivative, could you write in the comments, what do you expect, what do you imagine will be the pattern for the derivative of triple product? Wonderful, Muhammad, right? So it will travel through through the functions, and that's easy to verify. Here is the verification. It ends up being the prime is traveling through the functions. Yes, and you should try to establish it, right, guys? So I will show you in other lectures. You see, here is what I'm trying to teach you, if I can. That's truly the most useful thing to learn here, is that when you are understanding calculus, you are able to derive formulas that you never saw before. You are able to reach conclusions that nobody told you. Here is a conclusion, here is a rule. That means that you are thinking. Everything else that you are doing is just surviving a rather arbitrary class. So then we observed that we can figure out higher derivatives of a product, right? So f times g prime, it's f prime g plus f g prime. Now, if I take two derivatives, that's like taking the derivative of this expression, I end up seeing double derivative f times g plus 2, one's derivative of f, one's derivative of g, plus f, two derivatives of g. If I do it 3 times, I end up seeing this formula. Okay, and if you have ever played with expanding parentheses, you realize it's very similar. I hope you can see it here. Like it's called a binomial expansion. It's very similar to a binomial expansion. You see, x plus y squared, it's x squared plus 2xy plus y squared. X plus y cubed, it's x cubed plus 3x squared y plus 3xy squared plus y cubed. Do you see that this line here at the top of my screen is very similar to this line? Except instead of x cubed, I see triple derivative of first function. And instead of y, I see derivative of second function, right? So whenever I see y squared, it's double derivative of the second function. X squared, it's the double derivative of the first function. So the behavior on functions, the derivative acts on products of functions, just like binomial acts on expanding the sum of two terms to the power of n. And we can actually represent it by using this symbol. So this symbol, this means partial derivative, or derivative with respect to f, and this means derivative of g. So this is just derivative f, derivative g. And you can see that I just multiply it through, right? Distribute it. And I get this expression. You see that? Distribute it to fg, so that means that you take the derivative of f, this doesn't touch g. Distribute it through g, you take the derivative of g. Do you see this pattern, guys? And then if I square it, then look what happens. If I square it, it's the first thing squared, 2 times the product of them, plus the last thing squared. And so what you need to remember is for that Pascal's triangle. Do you remember Pascal's triangle? So that allows for very quick expansion. I can explain why that Pascal triangle works, but for that you need combinatorics. So if you go through my notes in probability, I can explain that. So this is the procedure. So you write 1, and then you have this pyramid here, right? And then the next layer, you put 1, and then look at it. Between two numbers on top, I add them, and I get this number. And I have 1 here, okay? So those are the coefficients of square. Now next is I put a 1 here. 1 plus 2 is 3. 2 plus 1 is 3, and then a 1 here. You understand? Look at those numbers are between two numbers above and below them. Yes? And then the next layer is 1, 4, 6, 4, 1. Could you, if you understand it, in my notes, write the next layer? Could you write the numbers for the next layer? What would be the numbers for the next layer of this pyramid? Okay, good, 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 wonderful. So some of you are getting it, yes? Good. Nice. And this is how it's used. Look at it, guys. How do I use this to expand quickly? X plus y to the power of 4. X plus y to the power of 4. I use this line, this coefficient. So it means 1 times x to the 4 plus 4. I just reduce the power of x by 1 and give the power to y. You see how it works? So it's x to the 4, x cubed, and y has the remaining powers. They just migrate to y. So that means 1, 4, etc. So how do you expand the x plus y to the power of 5? You just begin with 1 times x to the 5 plus 10 x to the 4 y and onwards, right? Just like the coefficients you had there. So you can use this to very quickly carry out multiplication. And that helps you to also calculate higher order derivatives. So this is what I ask you to do, guys. Can you please try to find the triple derivative of the product x to the 5 e to the x? Triple derivative. Can you do that? And do it fast. So I want you to find it's to Rachel. Do you remember how derivative work? How could it be this simple? It's product rule. You can write it symbolically. It's very useful to be efficient and write things symbolically. So what you do is say this is your function f, and this is your g, right? So what would the derivative look like symbolically? James, you are on the right track, but there you forget the coefficients. You are right, but you are forgetting coefficients. We mentioned that it's like expansion of power 3. Okay, good. Good. Don't get yourself confused, guys. Don't mix symbols with the final calculation. Good. So hopefully, guys, I'm really glad that those that came. I'm hoping that what I have in store for you will be very exciting, if we can actually get to that exciting point. All right, let's do it together. If you're not finished and you want to practice, stay after class. We can practice. Okay, guys. I tend to be bored by sitting and doing nothing here. So first, what do we have here, guys? So the formula that we're searching for is F triple prime times G plus, what do I write next? Plus, what's the next coefficient?
F double prime, and then G one prime.
And then don't forget there is a 3. Right? Because the expansion, the Pascal's triangle expansion is 1, 3, 3, 1. Yes? So it behaves like, again, you can verify that it's true. It behaves like, okay, so then the next would be plus 3 F prime G double prime plus F G and triple prime. Now, what is the triple prime of x to the 5, right? So here I have x to the 5. I take 3 derivatives. One derivative is I have 5 dropping. The next derivative I have 4 dropping, right? So it's 5 times 4, it's 20. The next is 3 dropping, right? So 5 times 4 times 3, what is that? That is 60, yes? So we have 60 x squared e to the x, because g is e to the x, plus what is if I take 2 derivatives of this function? So I have 5 and 4 dropping, right? 5 and 4. You are with me, guys? 5 and 4. It means I have 20. 20 times 3 is 60. So that is 60 x cubed. Derivative of g is just e to the x. It doesn't change. It's e to the x. Plus, if I take one derivative of f, that just 5x to the 4 times 3 makes it 15x to the 4 e to the x. And the last term is easy. I just take the derivative of e to the x a bunch of times. It's not changed. So it's x to the 5 e to the x. This is our solution. We can practice more problems of the sort after class if you're interested. Again, guys, so let's continue with the program. Well, I did it, and that's exactly what I did, Alisa. I did x to the power 5. I took the derivative once, the 5 drops down. I take the derivative again, the 4 drops down. Okay, so that's the product thing. And now very quickly, the quotient rule. I will not derive the quotient rule because I would like you to derive it. I would like you to derive it both by definition and geometrically. If you can do that, that means you master the geometric idea a little bit better and the definition idea a little bit better. So here is how you can remember this derivative. You see, guys? The derivative of a quotient, if you have one function dividing another, what you do is you take the denominator and you square it. Square the denominator. Good? And then copy the denominator and multiply by derivative of numerator. Just remember this step. And then you have minus, and then you have derivative of, they are reversed. You understand? They are reversed. So let's calculate this derivative, guys. This is the formula. I still keep it visible, but you should kind of know it. It's this guy squared, this guy copied, multiplied by derivative of numerator minus the derivative switches from numerator to denominator. Calculate the derivative of x to the 5 divided by 2 e to the x, please. Okay, James, be careful always, right? So something, I don't see an E on the numerator. There was an E in the denominator, there must be an E in the numerator as well. Thank you, Alisa. So we can practice again quotient rule and product rule in office hours if that's what you'd like to do, guys. Let's do it together. Here is the idea. Denominator must be squared. Denominator must be squared. You see, that's how I remember it. But I don't remember it. You know, if I forget the formula, I can derive it in 2 seconds, which is what you should do as yourself. So this function I square, I copy this function, and then I take the derivative of x to the 5 minus the denominator derivative times x to the 5. So what do I get? The denominator squared is 4e to the 2x. I squared it, yes? I get this denominator. Numerator, I get 2e to the x, derivative of x to the 5 is 5x to the 4. Minus, again, derivative of 2 times e to the x is not changed. It remains the same. Times x to the 5, which I don't differentiate. Good? And one last question. And this can be solved, of course, 2 ways, guys, right? So what is the derivative of 1 over x to the 5? Why does g remain the same as derivative? Because the derivative of 2 times e to the x is 2 times the derivative of e to the x. And e to the x is, the derivative of e to the x is e to the x. Yes, Alisa? Make sense? Yes, Minkowski. Correct. All right, guys, let's do it quickly together. So again, you might have observed that this is simply x to the power of minus 5. And taking the derivative of that, you drop the minus 5 and you have x to the minus 6. Yes? Good. You just drop it and you have the, but this is a power rule that we haven't established. We can use the quotient rule to establish that type of power rule. That's one way to do it. So here I do it using the quotient rule. You understand? I established that this rule is true. Yes, right? So I square the denominator and then I copy the denominator, multiply by derivative of numerator. Derivative of 1 is 0, minus the derivative of denominator times 1. So what do I get? I get simply, this is just 0. And here I get minus 5x to the 4 and x to the 10 on the denominator. I simplify and I get minus 5x to the minus 6, as expected. Here is one last problem for differentiation. Solve it fast, guys, because time is running and I'm bored. Oh, Alan, you're funny. Well then, what do we need to do, guys? The main operation is quotient law. So we square the denominator, copy the denominator, multiply by the derivative of the numerator, subtract the derivative of the denominator multiplied by the top function left intact. Okay, now in taking the derivative of this middle section, I will need product law, you see, because it's 2x squared plus 1 times e to the x. So here you're dealing with product law. Understood or not, I am moving to the next lecture. If you want to practice more problems like this, stay with me after class where I'll have more patience. Okay, so I need to cover the next thing.